Okay, so to learn how to construct space-time diagrams, let's start with a simple situation. And I apologize for having all this up on the view screen at once, on the slide at once. I actually wrote it out and recorded little bits and pieces of it, but then something happened and it didn't take, and I didn't want to rewrite this whole thing. So we'll go through this slowly. So the situation that we start with is over here. Okay, we have Bob and Anna that are standing a distance L apart. Okay, so I've labeled the x-axis here, and they're standing a distance L apart, and they're playing catch with each other. Okay, and the first thing is that Bob starts with the ball, and he throws a ball to Anna. He really zings it. He throws a fast ball. Okay, and so the speed is quite high, and so what we do is that we take this situation, this physical picture, and we convert it into a graph, a space-time diagram, where we plot. We have an axis here, a set of coordinate axes, where we have x on the horizontal axis and CT on the vertical axis. Okay, so again, CT has units of length, so both of these axes have units of length, and then we basically want to enumerate the events that occur when Anna and Bob play catch. So the first thing that happens is that Bob has the ball and he throws it to Anna, and at the moment that he releases the ball, that's an event. It happens at a particular point in time and a particular point in space. And if we basically arbitrarily set the x coordinate origin to Bob's position 0, and the time, and we just imagine that the clock, whatever clock we're using to measure time, doesn't start, or we call it time 0, we reset it to 0 when Bob releases the ball, then the coordinate of that event, Bob releasing the ball, is 0, position 0, x equals 0, and CT equals 0. Okay, so just like we would write coordinates on an XY graph or something, we just can enumerate this event with coordinates, and we can mark that. We can notate it. We can make a notation here for event A, which happens right at this point 0, 0. Okay. The next event that happens, the ball travels through the air. And the next thing that happens is that Anna catches it. Again, that's an event. Happens at a particular point in time, in a particular position, particular location. And since Anna is standing over here a distance L away, that happens at position L and at position at time T1. So the coordinate is C times T1. Okay. Now, what happens to the ball in between those two events, A and B? Well, the ball is traveling. Okay, and since we are only concerned with the horizontal motion here, in the motion along x, hopefully you remember from your first year physics that since the motion along x is not subject to gravity, in an ideal situation, there's no acceleration, and so it travels with constant velocity. And so since we're plotting CT over x, we should have some line, okay, with a particular slope which connects A and B as I've drawn here. Okay, and I've indicated it in red to correspond to the fastball over here. Now we can call this what we call these sort of the lines that connect events, or the lines on a space-time diagram that correspond to particular processes or movements, we call those world lines. Okay, so this is the world line of the fastball. I should point out that Anna has a world line basically that just goes vertically along L straight up, because she's not moving and she's not changing her position in time, and neither is Bob, so his world line goes straight up too. Now the next thing that happens is that Anna releases the ball after she's going to throw it back. Okay, but she's not going to throw it back fast. She's going to throw a slow ball. Okay, so she's going to lob it. So the x motion is relatively slow, and at the moment that she releases the ball, we have an event, and the coordinate of that event is L, because she's standing at L, and it happens at time T2, so the coordinate is C times T2.